All right, tonight what we're going to be talking about is solubility charts. And solubility charts come into play when you are dealing with double replacement reactions. And the reason why is because double replacement reactions require you to form at least one gas, liquid, or solid as a product. So you might be asking yourself, well, what would another product be if it's not a solid, liquid, or gas? And that would be something that is aqueous. Okay, so you can't produce only aqueous products and a double replacement reaction actually occurred. In this class, typically you will be mixing two liquids, and in these cases, these liquids are going to be aqueous, and they are going to form a solid. That solid is going to be, remember, a precipitate. So that's where that word came in from the signs of a chemical reaction. You need to form a precipitate for double replacement reactions to occur if you're combining two liquids. And what you're going to need to do is you're going to need to check the solubility chart. And basically a solubility chart, what it does is it tells you whether something is solid, which means insoluble, or aqueous, which means soluble. So is it able to dissolve? If it is, then it would be considered aqueous. If it does not dissolve, then that would be a soluble or a solid. So solid, once again, is insoluble, which means does not dissolve, whereas aqueous means that it was able to dissolve in the solution. And we will be giving you the solubility on the test, the solubility chart, but this is basically what one looks like. So how this works is you're looking at, these are soluble compounds, and soluble, another word for soluble, means aqueous. Okay, so what I'm saying is that if I partner up, these are the exceptions, if I partner up any cation or positively thing with nitrate, they will always be soluble, except, and there are no exceptions. So if I combined NO3 with Na, if I combined it with Sr, if I combined it with Pb, all of them always will be dissolvable, which means they will always be aqueous. Why? Because there are no exceptions. Okay, so let's look at another one. If I look at, let's say, chlorine. Chlorine follows the general trend that it is always soluble or aqueous, except when it is partnered up with silver, mercury, or lead. And during that case, it's going to be an exception, which means that these guys would actually be solids. Now let's look at the insoluble. So another word for insoluble is solid. So these anions will typically form solids except when they're partnered up with one of these guys. So if I look at, let's say, sulfur or sulfide, whenever it is combined with anything but ammonium, calcium, strontium, or barium, or the alkali metal cations, which are that first column of the periodic table, they will always be solids. If I had, let's say, lithium, though, with it, so Li combining with S, lithium is an alkali metal, so therefore it would be an exception. So instead of being a solid, it would be aqueous. All right, so let's try to use this chart for CaCO3. So I'm going to look at the anion, which is CO3. I'm going to find it on my solubility chart. CO3 is right here. So CO3 always is going to be insoluble except when it's partnered with ammonium and alkali metal. In this case, calcium is not an alkali metal. It is an alkaline earth metal, so therefore it is not an exception, so it will follow the general trend of being insoluble. Remember, the word insoluble means that it is going to be a solid. So these two questions are very similar. They're just using different words for the same thing. All right, now let's try NaNO3. NO3, according to this solubility chart, is always going to be soluble. And remember, soluble means aqueous. So there are no exceptions, so this would be soluble and aqueous. Now we're going to look at FeS. S is always going to be insoluble, except when it's one of those exceptions, and is iron one of the exceptions? It is not, so it is going to follow the general trend of being insoluble, which means that you are actually solid. All right, so where does this come into play? Well, what you're going to need to do for double replacement reactions is you are always going to now need to check your solubility chart. So I'm going to predict the products just like I normally would. So I have a compound plus another compound, so I know that that is going to be a double replacement reaction. So I'm gonna switch my metals just like I normally would for a double replacement reaction, and Ag is going to now go exactly where Ca was, so it's going to be AgC2H3O2, which is acetate, and then Ca is going to go where Ag was, so it's going to be CaNO3. Now I created two new compounds, so I'm going to have to worry about my charges. Ag has a +1 charge, acetate has a -1, so you crisscross and they reduce to 1 and 1. Ca, on the other hand, has a +2 charge. NO3 has a -1, so we're going to crisscross and we get CaNO3 2. Now I need to balance my reaction, and so in order to balance it, I'm going to need to put a 2 in front of the Ag C2H3O2 and a 2 in front of the AgNO3. Alright, so now I'm ready to actually be able to identify if this reaction occurs. See, this is a lot longer than single replacement. Remember, single replacement, all you have to do is check the activity series. You don't even need to predict products if it doesn't react. For double replacement, you're actually going to need to still predict the products, and then you can identify whether the reaction will occur or not. Remember, for a double replacement reaction to occur, I need to produce at least one solid. So I'm going to look at AgC2H3O2, or silver acetate. Oop, that should be a 2. So I'm going to look at my acetate. Acetate, as I look at it, are always going to be soluble. So that means that they are going to be aqueous, and in this case there are no exceptions. So I am going to label this, and you do it as a subscript, which I can't do with this pen. Okay, you're going to put AQ actually is a subscript right next to that 2 of the acetate, saying that this is going to be an aqueous solution. I now need to know what CaNO3 would be, or calcium nitrate, so I'm going to look at my solubility chart, looking at nitrate, and nitrate is always soluble and there are no exceptions, so this also I would label as a Q. Now, looking at how a double replacement occurs, remember, I need to produce at least one solid, liquid, or gas. In this case, I only produced aqueous solutions, so this reaction does not actually occur. Alright, hopefully you kind of have an understanding at least of how to read a solubility chart. We will be practicing more in class on whether and how to predict the double replacement reactions occurring.